Good morning. Welcome to this technical seminar on NASA Aeronautics contributions to the Ingenuity Mars helicopter. My name is Jeffrey McCandless. I'm the Associate Director of Aeronautics at NASA Ames Research Center in Silicon Valley, California. And I'm delighted to see that we have such a strong turnout for today's presentation. Right now we have over 100 people on the YouTube live link, which is terrific. This will be a great opportunity to learn about the upcoming flight and what it involved. I also appreciate the support of the NASA Aeronautics Research Institute, or NARI, for enabling this technical seminar today. Now, our plan here is to have 4 speakers go through their involvement with Ingenuity, and I'll introduce them now in order. We'll start with Larry Young from NASA Ames Research Center. He works in the Aeromechanics office, where he performs research on advanced aerospace system conceptual design, not only for planetary bodies, but also for work right here on Earth, such as aeromechanics and design for emergency relief and disaster operation and disaster response operations. Then we're going to shift over to Michelle Dominguez, also from NASA Ames. She's a Pathways intern, which is an amazing program that enables current college students and recent graduates to gain intern experience at a NASA center. So she plans to wrap up her bachelor's degree in mechanical engineering this year from San Jose State University. She not only has experience with the Mars helicopter, but she's also worked on the Black Hawk helicopter air loads data analysis. This past year, she received the 2020 Women of Color Student Leadership Undergraduate Level Award, and right here at Ames, she received the 2020 Ames Student Honor Award. And being a successful student, she wants to maintain that success, which is why she's going to leave a few minutes early. She won't be able to attend the questions and answers at the end because she has a midterm today, which is pretty important. And then third, we'll shift over to Dr. Brian Allen from NASA Langley Research Center in Virginia, where he works in the flight physics, the flow physics and control branch. He's worked on high-fidelity computational fluid dynamics for active flow control, and right now he's the technical lead for high-fidelity modeling within the revolutionary vertical lift technology project, which is appropriate since RVLT is one of the key sponsors for the work that you'll be hearing about today. And then finally, we'll wrap up with Dr. Carlos Malpica from NASA Ames. He's worked on flight controls and handling qualities for advanced rotorcraft, as well as handling qualities for passenger acceptance for air taxis. Right now, he's the technical lead for flight dynamics and control within the RVLT project. Now, while we're hearing from them, we have the opportunity, or you'll have the opportunity, to type in questions into a Conference IO window. So if you look on your YouTube live window right now, in the upper right, there's a link for Conference IO. And if you click that little link, you'll get a new window where you can type in your questions. And at the end, I will ask these questions to our speakers aloud, and we'll get through as many as we can. And then we'll wrap up this entire event at 9 a.m. Pacific time. So with all of that in mind, let's get this seminar off the ground. And we'll start with Larry Young. Larry, take it away.
Thank you, Jeff, for the introduction. Again, hello, everybody. Good morning. As Jeff mentioned, this is a development team that's comprised of JPL, NASA Ames, NASA Langley, and also AeroEnvironment, the company. This effort on the part of Ames and Langley was supported by the Revolutionary Vertical Lift Technology Project within ARMD. Next slide, please. So I'm going to start the presentation by giving some historical context as to Mars aerial exploration concepts and efforts, and then we will then transition into discussing the Ingenuity development efforts. So from a historical perspective, the majority of previously proposed aerial vehicles for Mars have been Mars airplanes. However, there have been many other vehicle types that have been proposed. That includes balloons, airships, gas hoppers, as well as rotorcraft. The Mars rotorcraft activity really only began roughly in the mid to late 1990s. And here at Ames, the efforts began in 1997 with a very modest center discretionary fund effort. Next slide, please. So the first planetary aerial vehicles would be the Soviet Union's Vega 1 and Vega 2 missions, where they released during entry 2 pressurized balloons, or each mission had 1 balloon, into the upper atmosphere of Venus. These balloons operated in relatively benign conditions in that they were basically flying at an altitude of about 54 kilometers. And so therefore the densities and the temperatures were much more benign than they would be at the surface of the planet, which is very hot and very dense with high pressures. Next slide, please. Next slide, please. Oh, thank you. So this next slide lists a partial survey of Mars airplane concepts. Literally, there have been hundreds of proposals, studies, papers that have been written and discussed on the topic of Mars airplanes. And this effort basically began in earnest after the Viking landers landed on Mars, roughly in the mid to late 1970s. And only then did we have a really good appreciation of how thin and how cold and exactly what the atmospheric composition, which was predominantly carbon dioxide, was. And so having that more realistic information about the atmospheric conditions, people embraced the challenge and began proposing various different approaches to using Mars airplanes and other type of flying vehicles. The first, this ranges from the work of Dale Reed at Dryden, now Armstrong Research Center, with his mini sniffer high altitude airplane efforts, and led all the way to the early to mid 2000s with the Ares, the Langley Ares Mars airplane. And one of the references here is Gwynn and Wright, Levin, and Rue. What you can see on the right-hand side, though, is basically kind of the trade between vehicle range or proposed range, the vehicle total mass. And historically, what you can see is initially the proposals were very ambitious with very heavy aircraft that could fly in long periods of time, at least theoretically. And as time went, basically, they became much more modest in their expectations in terms of range and trying to reduce the mass as well. Next slide. So arguably the most influential Mars airplane concept of all is the Dryden mini sniffer airplane. It's a vehicle that was in a series of aircraft that were developed, and actually this particular vehicle was proposed as both for high altitude, long endurance flight testing, but also ultimately could potentially be applied to Mars. And as such, it was designed to try achieving very high altitudes, and accordingly also use a unique reciprocating engine called an Ackermann engine that used a monopropellant using hydrazine to basically drive the propeller to fly at those altitudes. Next slide, please. I should note, though, there was a series of flight tests on that vehicle. It only had really achieved about 20,000 feet altitude during its flight tests. Now, there have been over the years, as I noted, literally hundreds of Mars airplane proposals, but therefore, this particular slide only just shows a relatively few, and they range again from the mid 1990s to the mid 2000s. Some of the work being done at Ames by Larry Lemke and Andy Gonzalez, all the way down to the bottom right-hand corner, which again is the Langley Ares rocket-propelled vehicle. This actually was proposed and almost selected as a Mars Scout mission, and additionally upon which it was one of the most well-developed of all the concepts, in that it received significant amount of ARMD support at the time. Next slide, please. So as I noted earlier, Mars rotorcraft studies really only started beginning to be defined and publications being presented roughly starting in the 1997 timeframe at Ames and elsewhere. And as you can see in this slide, from the very beginning, there was two fundamental approaches that one could take with Mars rotorcraft. One is to consider the vehicle as being an independent platform, flying and doing its missions by itself, or alternatively, as you can see here, the helicopter working in conjunction with a rover and or lander in a kind of a partnership, if you will, to conduct the missions that needed to be done. So even from the very earliest days, one of the key configurations that was studied, very similar to the current day Ingenuity, is the use of small coaxial helicopters working in conjunction with rovers, which you can see in the graphic on the slide. Next slide, please. So the work in the early years focused on critical technologies. You begin to see on the upper left-hand side the very first published Mars rotor test, a rotor that operated under Mars-like conditions, atmospheric densities, that was conducted here in Ames in the 2000 timeframe. On the left-hand side, there was an investment in terms of computational fluid dynamics effort, and these particular CFD pictures here are actually of the hover test on the left. And then finally, on the bottom left, you can see a small coaxial helicopter surrogate vehicle that we also used to conduct in the early days surrogate testing at Mars analog sites. Specifically, this site was on Devon Island in the Canadian Arctic. Next slide, please. So I'm now going to transition to Michelle Dominguez, who's now going to talk about the early days and of the Ingenuity program. And additionally, we'll talk about specifically some of the contributions that we performed in support of the Ingenuity development. So Michelle, if you could go ahead and take it away.
Thank you, Larry. So now going back 6 years ago, the Jet Propulsion Laboratory first proposed a small Mars helicopter. This proposed helicopter was intended to act as an aerial scout for the large rover in the 2020 Mars mission. And what started out as a technology development project later became Ingenuity, which is a small autonomous rotorcraft currently on the Red Planet. In order for the Mars helicopter to become a reality, JPL collaborated with other NASA centers, with Ames and Langley being involved since the early stages of the development. And as Larry previously mentioned, this Ames-Langley work was sponsored by the ARMD Revolutionary Vertical Lift Technology Project. Next slide, please. Here we have this picture that commemorates the kickoff meeting that took place at Ames between JPL, the Aeromechanics Office, and the RVLT project. Ames and Langley's expertise was requested by JPL to help address key Mars development questions. And in particular, they discussed concerns about low recirculation in test facilities and the appropriate testing required for that development. Next slide, please. The table here provides a general description of Ingenuity. It is lightweight at approximately 1.8 kilograms, and this is due to the majority of Ingenuity's components being graphite epoxy structures. Because Mars gravity is about 37% of Earth's, having a small mass helps. Ingenuity has two bladed rotors in a coaxial rotor configuration with a 1.2 meter rotor diameter. Its carbon fiber blades are very light, stiff, and have proportionally more lifting area than earth rotor blades. It uses solar electric propulsion with batteries storing the energy, and the solar cells are placed in a little beanie cap above the rotors, and they have a recharge time of 1 to 2 Martian days. Next slide, please. All right, now we'll watch a short video showing some of the capabilities of Ingenuity during an experimental test flight. As many of you know, Mars has gained 2 new residents this year, Perseverance and Ingenuity. The Ingenuity technology demonstrator will deploy from the belly of the rover with the intent to prove that flight on Mars is indeed achievable. Ingenuity will receive commands from Earth relayed through the rover, with each test flight performed without real-time input from Mars helicopter mission controllers. The first test will involve the helicopter taking off a few meters from the ground, hovering in the air for about 20 to 30 seconds, and then landing. And in later tests, Ingenuity will take off and survey the terrain from above. Its twin counter-rotating blades will fly in the thin Martian atmosphere at about 2,400 RPM. The rotor system must spin at this incredibly fast RPM to successfully generate lift, which naturally requires a lot of energy. Flight time is limited to around 90 seconds, but enable the helicopter to reach distances of almost 300 meters per flight at about 3 to 4.5 meters above the ground. Ingenuity is equipped with 2 cameras, one color horizon-facing camera for terrain images, and one black and white camera used for navigation. These cameras will give scientists a new perspective on the region's geology and allow them to peer into areas that are too steep or slippery to send a rover. Ingenuity will use solar power to charge its batteries and rely on internal heaters to maintain operational temperatures during the cold Martian nights. And here we see it landing. Next slide, please. This image is from the high resolution imaging science experiment on NASA's reconnaissance orbiter, which shows the Victoria crater, an impact crater at the Meridiani Planum near the equator of Mars. And it's obvious that a rotor would not be able to explore the crater or take pictures from the ground, hence why an orbiter took this picture. However, with a helicopter, the same scouting could be done in small number sorties. An interesting note is that it took Opportunity rover 340 sols to find a safe entrance into the crater to study the different layers of soil. A study showed that if a helicopter scout was available, it would only take 10 sols, which dramatically reduces the time for exploration. This is because the images from orbit do not have the resolution needed by the rover to safely enter the crater, whereas a helicopter scout would be able to provide the rover more detailed information about the terrain. Next slide, please. There was a number of aeronautics contributions supported by AIMS that included provided support of Ingenuity's air performance through a number of tasks, such as providing rotor design and peer review support, determining airfoil characteristics through 2-dimensional computation fluid dynamics modeling, using comprehensive rotorcraft analysis performance modeling for hover and for flight conditions, completing solar array interaction and sizing analysis in hover. Ames also completed in parallel and in-house the first ever surrogate Mars rotor testing for edgewise forward flight conditions. And this was accomplished in the Mars wind tunnel of the low pressure chamber in N242. Experimental results for this test were correlated with CFD predictions as well. Next slide, please. An example of correlation study using comprehensive rotorcraft analysis was performed by Perez, comparing simulated raw CFD data versus experimental data. And this experimental data was collected at Ames in the Planetary Aeolian Laboratory housed in N242, where we ran a surrogate rotor in forward flight under Mars-like conditions in the Martian surface wind tunnel. The bottom picture shows the Mars suite inside the facility. Testing consisted of both 2 and 4-bladed rotor configurations, with the objective being to test a nominal helicopter mode, as well as provide increased rotor thrust representative of the Mars helicopter coaxial design. The picture to the left is the 4-bladed rotor configuration tested in the Mars suite test section. And the plot on the right compares the experiment versus simulation rotor performance results of the 2-bladed rotor at Mars-like conditions as described by Perez. Ultimately, simulations with laminar flow conditions correlated well with the experimental data. And the cool thing about this is that not only do we have the capability of performing rotor testing in the Ames Planetary Aeolian Laboratory and Mars-like conditions, but we can use these experiments to validate our CFD simulations. Next slide, please. Another contribution from Aeronautics was the analytical and experimental studies of aerodynamics interference effects. Tasks for these included the analytical study of flow recirculation rotor system in the JPL 25-foot space simulator and other large vacuum chambers at NASA's NASA Glenn's Plumberg Station, Johnson Space Center, and Langley Research Center. The experimental study of flow recirculation of rotor systems in the JPL 25-foot space simulator, which we called the weather test, and the development of a time-dependent analytical wind model to incorporate the JPL Mars helicopter simulation for the simulation of vehicle hover behavior in the space simulator with flow recirculation. Next slide, please. So in winter of 2015, Ames conducted the weather test in the JPL 25-foot space simulator. And during this test, photos were taken of visualized rotor wake and flow recirculation as shown here to the left. Flow visualization was accomplished by using a grid of fluorescent tufts, which were located at a chamber corner on the floor closest to the test stand. And a fluorescent light source was installed in the chamber, and the images were captured in near darkness during rotor operation. The picture on the right side shows the setup for the weather test, which included a tuft rack, a sonic anemometer, and a test stand placed inside the chamber. The rotor was tested in upright and inverted orientations, with the expectation being that there would be a strong recirculation in the upright orientation and no recirculation with an inverted orientation. The tuft testing proved that an inverted rotor configuration resulted in absence of recirculation close to the rotor plane. The tufts also provided validation for CFD simulations. Next slide, please. Aeronautics also contributed to the facility development efforts through the conceptualization, developmental support and CFD analysis of the swinging arm approach for simulating vehicle hover response to winds, and alternate approaches to forward flight performance and system ID, which included custom wind tunnel designs, Langley transonic dynamics tunnel coast down from idle wind tunnel testing, rotating arm enhancements to earlier swinging arm test stand, and the JPL Caltech fan array. Next slide, please. And now I will pass over the presentation to my co-presenter, Dr. Brian Allen. Thank you.
Thanks, Michelle. So I'll be talking about the fluid dynamics contributions. I'll be highlighting the airfoil performance predictions and the vehicle simulations that were made for hover and forward flights, all in support of the Mars helicopter design and analysis. Next slide, please. So one of the biggest challenges to flying a helicopter on Mars is obviously the extremely low density of the Martian atmosphere, which is approximately 1% of Earth's density. So the low density of the atmosphere reduces the amount of lift that can be generated for a given rotor blade area. It also results in very low Reynolds number flows that tend to reduce the rotor performance. So the figure here shows the Mach number versus the Reynolds number, where the grade regions represent the most common areas of research for high-speed and low-speed aircraft. The open circles on the left side of the plot show the regions where we need airfoil data to run our rotor design and analysis codes. While there's some research at the low Reynolds number and low Mach number regions, there's very little data at the high Mach number, low Reynolds number regions that we need for our Mars rotor analysis. Next slide, please. So here is, while we need airfoil data for design analysis codes, it's very difficult to perform tests as it requires a very specialized wind tunnel that can operate these very low densities and Mach numbers up to 0.9. Fortunately, we did not have enough time to consider testing at these conditions to meet our design schedule, so we ended up using CFD to generate the airfoil tables that are needed by the comprehensive design analysis codes like CAMRED. And then the animation below shows the one of the flow solutions where you can see the laminar flow separation bubble on the back of the airfoil. Okay, next slide, please. So the airfoil simulations were performed using Overflow, which is a compressible Navier-Stokes flow solver developed at NASA. A paper by Koning and others give more details on these calculations. And the figures below show the hover performance for the airfoil, using the airfoil data generated by the CFD and the comprehensive code to generate the the rotor performance. So the figure on the left shows the rotor power coefficient versus the thrust, where the grade regions show the operational range of the helicopter and hover. The figure on the right shows the figure of merit, which is a key hover performance parameter versus thrust coefficient. So this analysis was very important during the design stage, since we needed to know if the rotor could generate enough thrust in the thin Martian atmosphere, and also to determine what the power requirements would be. So sometime later, after these predictions were made during the design stage, the rotor was designed and built and then tested at the JPL 25-foot vacuum chamber. And we were very happy to see that the predictions compared very well to the data. So while the predictions show good agreement with the experiment, there's still much that we need to learn about the flow at these very low Reynolds number, high Mach number conditions. And so if we want to consider future Mars helicopter designs, we really need to look at developing testing capability for airfoil data at these conditions for our rotor analysis and design tools, as well as for CFD validation. Next slide, please. So the CFD simulations of the entire vehicle were performed to better understand the effects of the solar array on the rotor performance, and also the aerodynamic loads on the array and the body for hover and for flight. So for this analysis, we used high fidelity CFD, since it's difficult for the design analysis tools to accurately model these complex flow interactions. Next slide, please. So for the three-dimensional vehicle simulations, we also used overflow as well. We used high-order schemes to reduce the dissipation of the tip vortices. The simulations were loosely coupled with a comprehensive rotor code, actually CAMRAD, to provide the rotor trim. In general, the simulations had about 98 grids, approximately 85 million grid points, and these simulations were run at NAS on 600 cores. If we use 600 cores, it may take about 2 or 3 days per simulation. And then the figures here show the surface grids that were used for the rotor, the array, and the cube-shaped body. Next slide, please. So this is an animation showing the CFD simulation of the Mars helicopter in hover at a fixed thrust condition. The upper left view shows the ISO surfaces of the vorticity magnitude shaded by the pressure coefficient, where blue is the low pressure and red is the high pressure. So this animation kind of highlights some of the interactions between the rotors, and also the complex flow interactions between the rotor and the solar array. Next slide, please. So the 3D simulations were performed at varying thrust conditions with and without the solar array. Our first simulations were performed using a solar panel based on an initial design size. As the vehicle design evolved, it was determined later that the solar array would need to be increased in size. There were some concerns that increasing the size of the solar array might impact the vehicle performance. And since we did this previous CFD analysis, it was fairly straightforward to go ahead and increase the solar array and then rerun the CFD analysis. So this figure shows a plot of the hover performance versus thrust, and it shows basically that the solar array had little impact on the rotor performance for the hover case. And then later on, once the vehicle, the rotor was built and tested, we were able to compare it to the data, and it showed very good agreement. So we were very happy about that. Next slide, please. So lastly, we looked at the CFD simulations for forward flight. Unfortunately, it was not possible to test the full vehicle in forward flight at the Mars atmospheric conditions and meet the design schedule. Therefore, CFD was key in providing some insight into the vehicle forward flight performance. This animation shows the kind of complex flow interactions that we see for the forward flight between the rotors and the solar array, as well as the cube-shaped body. All right, we can go to the next slide. So the CFD predictions of the helicopter forward flight, when we looked at the rotor performance, had little effect on that. We did, however, notice that there was an unsteady pitching moment on the solar array that increased with the increasing size of the solar array panel, but these were deemed to be within acceptable ranges. And you can see the plot below, which shows the regular size solar array in the green line, and then the red was a 5-centimeter extension, as well as I think the final one was the 10-centimeter extension, which is the blue line. So you can see the oscillations are much higher. There's a steady pitching moment there, but the design team felt that this was within acceptable ranges, so they were okay with that. Next slide, please. So I'll be introducing Carlos Malpica, who will be talking about the system ID analysis and flight control effects.
Very cool. Thank you, Brian. So Larry, Michelle, and Brian have illustrated some of the rich history of research at NASA on aerodyne flight on Mars, and indeed how recently through the Ingenuity program, ARMD played a key role supporting the conceptualization, supporting the analysis, and supporting the development of facilities to conduct the validation of Mars helicopter performance and flight mechanics as well. In the realm of flight mechanics, one of the key questions is what are the control gains that you need to stabilize the vehicle? And that is a reality of helicopter flight. All helicopters are unstable open loop. Now on Earth, once you have a prototype that you deem safe enough to fly, you go out there, you fly it, you inject frequency sweeps, and you do a system identification in flight of the vehicle that allows you to optimize the feedback gains for your vehicle. So clearly here we didn't have that luxury. One aspect is trying to offset the gravity, which you can get around by offloading some of the weight from the vehicle. But then, it gets tricky to try to match all the moments of inertia for the rotational dynamics. And then there's the aspect of the air density. So, okay, so one option is to fly at 100,000 feet above sea level. If that doesn't work for you, then you need to find a vacuum facility that can still blow air at the very low speeds that were required to match the operating envelope of the vehicle. And that in itself was a challenge. So we did have to come up with this contrived system identification setup using a combination of swinging arms and wind walls, what we called wind walls, which are effectively an array of fans inside the vacuum chamber, in order to generate airflow over the rotor and to be able to tease out piecewise the key flight mechanics parameters. The significance of trying to blow air is that the instabilities of the helicopter become stronger in forward flight. So that was a crucial aspect of the testing. Next slide, please. But why go to this level of investment? The video that's playing will show eventually why. This is a very early attempt at trying to understand the problem. The helicopter is lifting off the ground, so we're clearly generating enough thrust. The problem is not generating the lift. It's that the helicopter became unstable the moment we took it to a lower density. The same helicopter operating at lower rotor speeds at Earth densities was perfectly stable, very easily controllable by a human pilot. But as soon as we took it to the lower density, it became unstable. So clearly we had to go back to understand some of the fundamentals of the flight mechanics in the Martian atmosphere condition. A common bad habit in aircraft development is to defer design decisions to later stages, assuming that the controls people will be able to fix it. In this case, we had to factor in the control aspects from the beginning of the design process. Next slide, please. So we set on the path to demonstrate that controlled, and the key word there is controlled flight in Mars-like atmospheric conditions was feasible. And this was the prototype vehicle that we used for that enterprise. A key aspect to note of this prototype vehicle is the rotors, which are essentially the same rotors that went into Ingenuity. Another aspect of the prototype is that we offloaded a lot of the weight from the vehicle. So sensors, batteries, the computer, all the avionics, all that stuff was offloaded onto the ground, and the control and the power signals were routed up to the helicopter through the electrical cables that you see hanging underneath it. In order to track the attitude of the vehicle and the motion of the vehicle, there were these little balls here, which were the trackers for a Viking vision system that tracked the position of the vehicle inside the chamber at all times. Next slide, please. Now the path to eventually free flight of the vehicle started with the modeling and simulation of the flight dynamics of the vehicle. using established rotorcraft flight dynamics principles, classic textbook stuff. We then subjected the helicopter to a system identification test campaign to validate the model and identify any corrections that were needed. Per usual, the complexities of modeling the rotor wake dynamics reared their head. They're complex to model even in a static or steady condition, but the unsteady characteristics of the wake that as it relates to the maneuvering of the vehicle are even harder to model, and especially to model in real time, which is a key characteristic of the simulation models that are needed. But in the end, we were able to adjust the models to account for all the differences that we found and explain the dynamics effects that were missing. One of the biggest uncertainties was whether we would have sufficient stability margins to close the attitude feedback loops. As I mentioned earlier, rotorcraft are always unstable, open loop unstable. That's one of their biggest characteristics. The biggest source of damping is from the aerodynamics, and at the densities of Mars, damping was significantly reduced, and that affected the design of the vehicle to the point where we were pushing the boundaries on whether we would be able to stabilize it or not. But we were able to. We found that we had enough margins, and we were able to design the feedback controller that eventually allowed us to fly the vehicle in the chamber. Next slide, please. Just sort of a look at the specific system ID process, where we first took the helicopter on a force torque sensor, and we injected perturbations into the actuators and the rotors to measure the force and torque responses. We then mounted the vehicle on a swinging arm in an attempt to try to generate translational motion and flow over the rotors. And then the last step was mounting it on this gimbal, and we injected frequency sweeps into the actuators. We measured the rotational dynamic response, and from that we were able to identify the key dynamic parameters that govern the instabilities of the vehicle. And the last step was then to take it into free flight. So next slide, please. So the video here shows that key toll gate. Without this flight, the program would have not gone forward. The reason that this flight was successful, and we demonstrated successfully demonstrated controlled flight in Mars densities, is the reason that the program was able to go forward, and we have Ingenuity flying on Mars, or hopefully flying soon on Mars. You'll see the vehicle moving around a little bit in the chamber. That is the effect of the recirculating, self-induced recirculating turbulence inside the chamber. But the control system was holding position within the designated required tolerances. Now you'll see it come back down for a landing. Okay, next slide, please. One of the key deliverables of the project were the updated simulation models, and these were then used extensively to simulate the different flight profiles that the vehicle will be asked to execute, hopefully next month, on Mars. They ran, and this was run by the JPL guys, but they run countless and countless of Monte Carlo runs, trying to, ascertain the probabilities of anything going wrong. But that effort was enabled by the updated flight dynamics models. Next slide, please. So some key timeline issues. So Mars 2020 launched last year on July 30th. And as many of you may be aware, it successfully landed on February 18th of this year. Since then, the rover has been moving around the surface of Mars and executing its checkouts and all its processes. It is my understanding that April 8th might be and I haven't seen anything official. This is just what we're hearing. April 8th might be the best chance for first flight. But we did have confirmation that the protective shields have been jettisoned from the rover, and that a site for where the rover will drop the helicopter has been decided. Next slide, please. And of course, this was, this was an absolute team effort. It was an effort led by JPL and the early proponents of it. And here's some of the names of the key people, but next slide, please. As always, there's an army of unnamed young engineers, interns that helped through every step of the process, and a deep. One of the coolest things of this project was actually seeing this generation of young engineers getting energized about aerospace engineering. And that's one of the longest, in my opinion, one of the longest standing benefits of this project. Finally, I'd like to acknowledge and thank the Public Affairs Office at Ames and headquarters for enabling this seminar, and in particular Nari and Raj and Michael for their support with the logistical coordination that allowed us to run the seminar today. Next slide, please. And here's a couple of links that you guys may choose to search. They'll have more information about the vehicle and the mission. Thank you.
Fantastic. I appreciate all the insights we've gained from these presentations so far. This is definitely informative. And now it's time to hear from you. And so the Conference IO link has a number of questions already posted, and you can read through those questions. And on the left side, there's up arrows, so you can upvote questions. And I'm going to try to get through as many as we can, starting with the top question so far. And I'm going to merge a couple of these. So one of them, this deals with landing. And the question is, can the helicopter land and take off at an angled surface? And what happens if it lands on a slope? And then a related question is, do the landing feet handle Mars conditions well? Can you answer that question?
Yeah, let me take that one. AeroVironment, as part of their hardware development efforts, actually did an extensive series of landing leg simulations of landings to help define and refine the landing legs for the vehicle. And so they looked at a variety of slopes. They looked at a variety of different surfaces, including obstacles, rocks of certain size, in evaluating that. And that did have, a significant design input into things like the elastic hinges that join the legs to the fuselage body, out of what stiffness is used to define those, as well as the angle and display, if you will, of the landing legs and the heights of the fuselage with respect to the ground to get the best design for that. But the short answer is yes, we looked at it. In terms of the, the little tips on the landing legs to support it on the surface of, dusty surfaces, there was a fair amount of thought that went into that. Originally, the idea was to use some fairly rounded type of shapes, and you'll see that there's kind of more of a spatula type of shape on the end of the tips of the legs if you look at them closely.
Got it. Thank you, Larry. The next couple deal with wind. So the top question now is, what is the wind limit for flight? And then a related one is there wind on Mars, and do you need to take into account gusts that may occur to assess helicopter stability?
Yeah, that sounds like I should probably take that one. So yes, winds are a factor. The operational envelope of the vehicle was tested up to 30 meters per second. That and the reason for why it is important is because I mentioned the inherent instability of rotorcraft. This instability becomes much stronger at higher speed. That's one of the reasons that helicopters on Earth have tail empennages, because they help alleviate that instability. But Ingenuity, being a coaxial, does not have that benefit. So yes, there is a wind limit beyond which we would not operate, and weather forecasts will be relayed from Mars to Earth before decisions about flight are made. As far as gustiness, the vehicle, it's the same premise. You'll have weather forecasts that will determine whether it's safe to operate or not, and so there will be a go no go decision based on that. But in general, the vehicle has a very decent disturbance rejection characteristic, and it can fly in reasonable turbulence.
Got it. Okay, that helps. Thank you. Next one is, can you comment on the difference between supporting a spaceflight mission versus usual aeronautics research?
So could you repeat that, Jeff? I think you said,
Yeah,
what
sure.
are the difference?
Yeah, it's fine. Can you comment on the difference between supporting spaceflight mission versus usual aeronautics research? So
yeah, I think I could briefly speak to that. So basically, among the other things that you have to take into account is definitely things like stowing the vehicle on the rover in the aeroshell. That's a big consideration. You also have to account for launch loads in terms of the G levels, the acceleration levels do during the vehicle. Folks, in terms to get across.
okay, we may have lost Larry's audio there. Oops, but I think my audio is working. All right, so tell you what, we're gonna shift over. So I think my audio is still working, and we may come back to that on when Larry's audio is back up again. But in the meantime, why don't we press on here? Let's talk about power. How many watts are required to hover Ingenuity on Mars? Can anyone take that one? And this might be a question for Brian or Carlos, if possible. if you know the answer to that one.
Yeah, it'd be hard to remember the number of the top of my head, but you know if people wanted to go to the Aeromechanics office branch website, all our papers are there, and I'm sure we can find that number. Yeah, but coming up with the numbers specifically off the top of my head right now, I'd be hard pressed.
Okay. All right. Fair enough. All right. Let me press on here. Okay. What about a bad day? What about with crashing? Can the helicopter withstand a crash to a certain degree?
So, I'll emphasize that ingenuity takes success one step at a time. Every little step that it does is taking that success because it is another opportunity for learning about the challenges of flying a helicopter on Mars. So, if ingenuity crashes, it will have still been an opportunity to learn about the risks involved in flying the helicopter. Now, will it survive a crash? No, it's unlikely that it would survive a crash. If it tips over and the rotors are spinning at high speed, there's no chance of coming back from that. But again, this is about exploring a new frontier, and every step of the way we're learning new things. So by that measure, it's always success.
Got it. Okay. So then a related one is, and maybe this is a little more general, how does a helicopter protect itself from the harsh environment on Mars?
Okay, I have to think about that one for a second. One feature that the helicopter does have is that it needs to survive the harsh winters, the cold temperatures. So it is in fact equipped with heaters that will keep the key components warm throughout the cold spells on Mars. That to my in my recollection is the harshest environmental concern that ingenuity would face. But I don't know if we have Larry back online. He might have other. Is Larry back online?
I'm online. Can you guys hear me now?
Yes, I can hear you.
So I'm sorry, I missed the question. Can you please repeat that?
So the question was, what type of mechanisms does Ingenuity have to protect itself from the harsh conditions on Mars? And I mentioned the protection from the cold temperatures.
Yeah, okay. So you talked about the survival heat and how that's a very large fraction of the battery charge. Yeah, the other thing is that AeroEnvironment in particular had to look at a variety of different seals that had to be applied to bearings and other, mechanical components like that. The other, including the servos and the electric motors that are on board the vehicle. Additionally, one of the considerations of having the thin mylar siding on the fuselage cube is, one, to provide an air gap for, minimizing the necessary survival heat power required, but also it has a protective function in terms of keeping dust and other dust from getting into the electrical components of the vehicle, which are all in the fuselage cube.
Got it. That helps. All right. Thank you, sir. All right, I see that it's now 9 a.m. Pacific time, so we are wrapping this up. Once again, I appreciate all of the audience questions and all of the audience participation, and especially appreciate our speakers, as well as NARI for supporting this, and RVLT for additional support with all this collaboration across NASA. This is very much a team effort, and it's worked out fine. So go Ingenuity. Thanks for participating, and we'll talk next time. So long.
Thank you. Bye.
Thank you. Bye.